All right, guys, back again here for video number 2, and we are going to start with acceleration. Acceleration is kind of difficult for us because there's a lot to think about when we do our acceleration calculations. But if we just stop and thought about what the formula was and plug those numbers in, I think we'll be all right. So the formula for acceleration is final speed minus initial speed divided by the total time, or velocity final minus velocity initial divided by time. So let's apply that. After 2 seconds, Isabella was riding her bicycle at 3 meters per second on a straight path, reminding ourselves that to find acceleration, we need to be moving in a straight line. After 5 seconds, she was moving at 5.4 meters per second. What was her acceleration? So we're going to have speed and time. So we're looking for our final speed. So I'm going to look through here. 5.4 meters per second is her final speed. So that's going to be the first number that I put in my equation. Now I'm going to subtract off what her final speed was, 3.0. Subtract off 3.0. So 5.4 minus 3.0 is 2.4. I'm going to erase that so we can see that. Go over that one more time. Pink. All right. Here is her final. Here is her initial. I'm going to subtract final minus initial, 2.4. Now I need to look at my time. After 5 seconds, so that's her final time, subtract off her initial time, and that gives us 3 seconds. So now I'm absolutely going to use a calculator for this. 2.4 meters per second divided by 3 seconds gives us 0.8 meters per second squared. Acceleration is always a squared unit. We're not able to cross off like units like we are for the distance, speed, time triangle. So we can either write it 0.8 meters per second squared or 0.8 meters per second. So remember when we were doing this, when we first started learning how to do this, and we would draw our line, and it would help us visualize what we were subtracting. So we would draw our straight line. Okay, and we would start to plot the information from our story problem. After 2 seconds, so I'm going to put my time on the bottom because that's what I have to do with my story problem, with my formula. After 2 seconds, Isabella was riding her bicycle at 3.0 meters per second. I'm going to put my speed up on top because that's what my formula asks us to do. After 5 seconds, so now I'm going to plot that, 5 seconds, she was moving at 5.4 meters per second. What was her acceleration? Alrighty, so now I have all of the information on my line here. So I'm going to subtract final minus initial. So 5.4 minus 3.0, giving me 2.4. Final speed minus initial speed. 5 minus 2 is 3. And I would divide that out, and I came up with 0.8 meters per second squared. Now, that is positive acceleration because we are speeding up. We're going to have story problems where we're going to have negative acceleration, where we're slowing down, where our final speed would be less than our initial speed. So it's not always largest minus smallest. You need to look at what was the final speed, subtracting off your initial speed. And then same with your time. Okay? Alrighty, so let's erase that so that we can see this graph below. Okay, here we go. You are standing at the corner of River Street and 3rd Street. A friend calls and tells you to walk 3 blocks west of your present location to meet her in which building is your friend? Okay, so you're right here. That is your reference point. That is your starting point. You need to have 3 things to describe the location of an object. We have one of them right here, your reference point. Now we need to have distance and direction. 3 blocks, 1, 2, 3. That's our distance. West is our direction, and we are at the grocery store. All right, so when we look at these graphs, you're going to need to interpret what's happening with them, as well as give a real world application. So the ideas that we look at are right here. At rest, so that's stopped. Constant speed, speeding up, slowing down. All right, so on a distance time and speed time with slowing down, that over time our distance is getting shorter, so we're slowing down. So a real life application might be we are approaching an intersection. We're turning a corner. We're pulling into a garage. We are entering a roundabout. Anytime when we need to slow our speed down, this is what the graph would look like. Another graph that we might have is an object at rest, no motion. That over time here, there is no speed. No speed. So that object is at rest. Here, the distance is the same. Over time, the distance is the same. So this object here must be at rest because there is no change in the distance. The real world application for that might be that you are stopped at a stoplight, or you're parked in a garage, or you are at a drive-through, you're parked at Target. Wherever an object has no movement, no speed, it's at rest, it's going to look like this. Okay. So then we have another graph. We have constant speed. So in this moment, we're going the same speed. In this moment, we're going the same speed. In this moment, we're going the same speed. Constant speed. If we were to calculate all of these right here, we would be able to see that if we divided distance divided by time, we would come up with the same number, whether that's 30 miles per hour or 50 miles per hour or 10 miles per hour. Okay, 1, 10, 2, 20, 3, 30. This is just a rough example that if we were to divide distance divided by time, this would be 10 meters per second. 20 and 2, also 10 meters per second. 30 and 3, also 10 meters per second. This is constant speed. So any time where you are able to move without having to slow down. Cruise control on I-65 was the example. Here is our final graph. Let's do our final color, and that is speeding up. We're speeding up. That over time we're getting a little bit farther away. Speeding up. So our real life application would be we are leaving that intersection or stop sign that we were previously stopped at. We're merging into traffic. We're pulling out of the garage. So be able to identify the graph and a real world application. Okay, which line represents the fastest speed? That is going to be A. Justify your answer. Just writing the letter A down is not going to cut it. You need to say why. Line A is the fastest because it is the steepest. Anytime you have a steep slope like this, that's going to indicate a faster speed. Just like we talked about today, line A covered more distance in a shorter amount of time compared to B and C. So let's say we are going to say that this is 50 kilometers and it took line A maybe only 1 hour to get there. If we have line B, if we continued on until it got to 50 kilometers, that might be 3 hours. And then poor line C, if we continued until it reached 50 kilometers, that might be something like 5 hours. So line A covered more distance in a shorter amount of time compared to lines B and C. All right. Mr. Shelp ran 5 kilometers from his starting point in 2 hours. If he continues at the same average speed for another 6 hours, how far will he have traveled from his starting point? Show your work. All right. Super important here is to figure out what he does in 1 hour. So we're trying to find out how fast he can run. 5 kilometers in 2 hours. Divide that out because we need to figure out what it is per 1 hour. 2.5 kilometers per hour. That's how fast Mr. Shelp was run. Now, we need to apply that rate right there to how many hours he is running total. We have 2 hours here and 6 hours here. So a total of 8 hours. Mr. Shelp is running for 8 hours. He is very tired. So 2.5 kilometers per hour times 8 hours gives us 20 kilometers. That is how far will he have traveled. That is distance. And distance is, we're trying to figure out how, we're figuring out, speed times time. We're figuring out what his distance is. So we're covering up that triangle here. And we are multiplying our speed and our time together to give us our 20. If you're comfortable and understand the idea of proportion, this is what you know. 5 kilometers in 2 hours. You're trying to figure out how many kilometers would that be in 8. Cross multiply. Divide each side by 2 to get rid of that 2, leaving x by itself. 20 equals x. You must know how to do this. Remembering that you find out per 1 hour and apply that to how many hours is in your story problem, What are the 3 things needed to describe the position of an object? We need the distance, the direction, and the reference point. What 2 things are needed to describe the velocity of an object? We need speed and direction. What are 3 ways an object accelerates? We speed up, we slow down, and we change direction. So to wrap this up, we're going to look at these scenarios with these cars. Each car is traveling at 50 kilometers per hour. Do they have the same velocity? Why or why not? All right. To have the same velocity, we have to have the same speed and direction. They both have the same speed, so we're good there. But guess what? Not the same direction, so they do not have the same velocity. So let's take a look at this one. Car on the left is traveling at 65 miles per hour, and the car on the right is traveling at 60 miles per hour. Do they have the same velocity? Yes or no? Why or why not? Well, they do not have the same velocity because they don't have the same direction. They have different speeds. They have the same direction, but they have different speeds. So the velocity is not the same. Same speed, different direction, no go. Different speeds, same direction, still no go when it comes to do these cars have the same velocity. Well, I hope this helps, and make sure that you review your study guide and do the quizzes and do the Kahoot and review your vocab or your outline notes. Set yourself up for success for the test that's coming up in a couple of days. All right. See ya. Bye-bye.